My name is Saadat. I'm working as a postdoc in one of the best university in Korea, Yonsei University. I'm a KRF fellow here, and next month I'm leaving actually Korea. I'm going to China. I will be working in Nanjing Forestry University as an associate professor there. So, yeah, thank you. So I'm going to talk about not about the carbon, but other side. Another element is nitrogen, and not in the nutrient cycling, but the end product of nutrient cycling, which can be a dangerous product like N2O, which is a greenhouse gas. You guys all know. I will be talking about the combined application of organic manure and fertilizer and how it influences the nitrous oxide productions. So coming to the background, actually, we all know that why we use synthetic fertilizers. These are necessary evil. We need them to get highest yield with the most economical way. Of course, they have a lot of issues, especially regarding the soil health, and also about the other pollution like environmental costs like N2 emissions and nitrate pollution. What about the other side? If the other potential way is we replace fertilizer with organic amendments, however, we don't get agronomic yield as we can get with the synthetic fertilizer. And yeah, of course, it improves the soil health on the other hand. And what about the combining these two techniques? So we can get high yield and we can reduce some of the detrimental effects of fertilizer with that. However, we don't know about the environmental cost of this combination as well. So there are papers, of course, but when I talk about environmental cost, for me it means actually nitrous oxide. So you will find less number of literature on nitrous oxide emission. How, when we combine these two techniques, what could be the results out of that? And another technique which is proposed here and many other times is why we don't replace the organic amendments with biochar. And we can get, when we combine fertilizer and biochar, we can get high yield, we can improve the soil health, and there are some laboratory-based studies, even by me as well, that says that biochar suppresses nitrous oxide emissions. Why don't we combine these two techniques and get the benefits? But what about the cost? So based on these backgrounds, actually, I had, for this field study, which I'm going to present today, I had two objectives actually. So the first thing is when we combine these techniques like manure, here I use livestock manure and poultry manure, and a biochar, here I use actually a peanut shell biochar. When we combine them with fertilizer, how they influence on the fluxes of the N2O, but most importantly, if fluxes is being changed either by suppressing or being promoted, what is the mechanism? How these things are changing the N2 emission and why they are changing it, right? So that was my main question, and to answer that, actually, I used two techniques. First was, of course, molecular technique. I used quantitative PCR, and I targeted only those functionalities like ammonium oxidizers, N2 producers, and N2 reducer for the case of denitrifiers. And my main target was only three processes like nitrification and denitrification or nitrifier denitrifier. These are, we normally consider these three mechanisms as responsible for N2 emissions coming out of the soil. And the other technique I used was N2 isotopomer actually. The linear molecule of N2O contains two nitrogen atoms, and the differences of the heavy isotope on alpha side or the beta side. So the differences is called site preferences, and the studies based on the pure cultures of these organisms like denitrification and nitrification, they found that the SP values of N2 produced by nitrifiers or denitrifier, actually it differs in SP values. So using this method, we don't have to disturb the soil, we just collect the N2O, the gas products, and we can tell what are the mechanisms behind the emission of those N2O. However, there is one issue, as you can see in the last, there is N2O reduction process actually, which changes the SP because these enzymes, they prefer lighter isotopes. So for this study, I did not use it as a quantitative tool, I use it as a qualitative tool. to differentiate who is producing N2O inside the soil. So we did a field study here in Korea. Our field study was in Chongcheon, Namdo, as far from Seoul, and I targeted four treatments there. Of course, our control was also fertilized, while our treatments were like two manure and one biochar treatment, equally fertilized. So it was a combined application. The crop we used was sweet potato, and I just monitor N2 emission and of course the changes in microbial community during one growth season of that crop. And yeah, here you can see some collaborators as well. So nitrous oxide, what I use, of course, static chamber system, and I analyze it in GC. For isotopomere analysis, we sent our samples to Hunan Institute of Climate Smart Agriculture in Germany, and of course, microbial community and soil characteristics were done by me in Yonsei. So coming to the results, the first main results, of course, was temporal N2 emission fluxes. What happened? You can see there were considerable, you can say, statistical differences. Of course, N2 is a crazy gas. Actually, you don't get proper differences through temporal levels. So because it depends on the hot spots and hot moments. Moisture is playing a very important role in N2. N2, you don't find very clear differences like CO2. If you add something and you can see higher CO2 emission in amendment soil, but N2 will not behave in that sense. It will be totally different. So it's good to see N2 emissions in a cumulative scale. So how actually on a cumulative level, what are the impact of your treatment on N2 emissions? And here you can see that our manure treatments, they had significant effect on N2 emissions. Emissions were much higher compared to biochar, of course, and also the control. So the question was, N2 emission is increasing in these manure treatments. What is the reason? Is there any shift in the microbial community, or are the background processes? So to understand the background process, I just use site preference values, and here you can see there is no significant differences on 6 big events of N2 emissions. I analyzed them isotopically, and there are smaller differences, but they all are not statistically, they are not they are insignificant. So the main point is the combined application when we are doing actually is not shifting the dominant pathway, whoever it is, either denitrification or nitrification. So that's the next question. Who is actually responsible? Is it nitrification, denitrification, or nitrifier denitrification? Here we normally use this kind of plotting. It is difficult to see, I guess, right? So I tried to show it just in one graph. Here you can see. And what comes with this result is actually the dominant pathway you can see was mainly denitrification, because isotopomere analysis here SP values are very close to denitrification level. Yeah, some are showing even N2 reduction, but overall what I concluded with these results that denitrification was the dominant pathway, and it did not change with our amendments. So it remained as it is. But however, N2 emissions were increasing. So the question comes, why N2 emissions were higher? Is it just a substrate effect, like we had nitrate, we had ammonium, we had DOC, of course, with the manures? Is it just because of that? Or there were some serious changes actually? I can only say here that there was no linear regressions between N2 emissions with mineral nitrate or ammonium, even DOC. In some treatments there was, but most of the treatment there was no significant linear regression between these two. So my target was actually the community. For this column graph, just I wanted to show you one thing, is AMO, ammonium oxidizers. Of course, they were not changing. So it supported the results of SP values that in ammonium oxidation was not the dominant pathway. Of course, denitrification was the dominant pathway. And my treatment showed denitrification community was shifting. However, the shift in denitrification does not always mean that N2O will increase, because denitrification is not only the source of N2O, it is actually a sink of N2O as well. The last step of denitrification is N2O reduction. So when we look at the denitrification, we don't look at the, okay, the appendice, we look at the ratios between the appendices. And here you can see that the ratios actually, N2 producer between N2 reducers actually, my manure treatment showed a significant change. It means that N2 producers, they increase much higher compared to the N2 reducers. So that big shift actually causes the N2 emissions. So that's the conclusion of my talk here actually. And concluding that, but we recorded increase, of course, N2 emission rates in livestock and poultry treated plots without causing change in the dominant pathway. And isotopomar of soil emitted N2 sampled at 6 different intervals. They pointed that denitrification as the dominant pathway in all treatments. Increase in relative abundance of actually only one type of denitrifier. It was NIRK containing denitrifiers. And their abundance was increased, almost it was doubled. However, careful evaluation, we suggest that combined application management approach is necessary. You cannot just suggest based on the crop yields or something else. And here I also wanted to add that long-term field studies actually, they suggested that the manure normally change the basal emission rates of a soil. And in my study, I suggest that the emissions the basal changes are caused by the community shift. The relative communities in denitrifiers is changing, and it is promoting N2O producers compared to N2 reducers. That could be one of the reasons. So thank you very much.